Hey guys, let me pull up next section. We're going to be looking at 4.2, the mean value theorem. Some similarities to what we've been doing in 4.1 and 4.3 a little bit, but definitely kind of takes its own, does its own thing. And so that's why I separated it from those two. Okay, let's check it out. The mean value theorem. We're going to begin, we're going to build up to the mean value theorem by talking about this other theorem called Rolle's theorem. So Rolle's theorem says this: if f of x satisfies the three hypotheses, these three hypotheses, number one, that f of x is continuous on the interval from a to b. Number two, that f of x is differentiable on the same interval from a to b. Notice it's really just a nuance, really makes no difference for our problems, but notice that f of x will be continuous on the closed interval a to b, including the endpoints, but it only needs to be differentiable on the open interval from a to b, which does not include the endpoints. Again, just a nuance. We're gonna make sure that it's continuous at the endpoints themselves, but it doesn't have to be differentiable at the endpoints themselves, so long as it's differentiable at all of the points between A and B, that will be fine. Okay. And number three for Rolle's theorem, that f of A is equal to f of B. In other words, the y values of the endpoints have to be the same. Okay, so if it's continuous on the interval, if it's differentiable on the interval, so continuity, right? We look at these, if we think about these a little deeper, continuity would mean there's no holes, there's no jumps. Differentiable means not only are there no holes or jumps, but there's no cusps, there's no vertical tangent lines. And the y values of the endpoints are the same. If all that's true, then there exists C in that interval from A to B such that f prime of C equals 0. Okay, so this is like a classic example of a theorem in calculus that seems really complicated and really heavy and a lot of detail and a lot to kind of hold together in your mind. And then there's this conclusion, you're like, what? Like, okay, if you say so, right? But if you look a bit deeper and maybe do some drawings, then you realize, oh, well, yeah, I mean, of course, this would have to be true. And it's almost like you wish you had lived back then and you could have come up with this and put your name on it, because, and you would be remembered forever because it's like so obvious. Okay, so let's get some drawings. So we'll look at the first one, a little bit simpler. So there we have the one on the left, right? So we have this function. We're only looking at it from A to B. It's continuous, right? It's differentiable. There's no cusp or anything. And the y values are equal. Okay. So what we're saying is somewhere between A and B, there is an x coordinate, we'll call it C. There's somewhere the derivative at C is equal to 0. Hey, as you look at this, would you say like, is somewhere the derivative is 0? Well, yeah, of course, right? If the y values are the same at your starting and ending points, and it's continuous, and there's no cusps or vertical tangent lines or anything, like no jumps, right? There's nothing like that. Then of course, if it goes up, then it's going to have to come back down, or if it goes down, it's going to have to come back up. And at some point, you're going to have a horizontal tangent line where the derivative equals 0. And yeah, and we can see it. Okay, it's maybe about right there, wherever that peak is. It's a little bumpy in my drawing, but you know, maybe it's about right there. Of course, that would have to be true. Things could be a little bit more complicated, you know, really stretching the word like a little bit. What if it doesn't just go up and back down, right? What if it kind of wiggles around a little bit? So let's say it drops down and then goes back up and then goes back down and back up. Well, does there exist a C between A and B where the derivative is 0? And you're like, well, yeah, of course. In fact, it happens 3 times here, right? One at the bottom, that first, local min, and then at the local max, and then the next local min. There are 3 different C values. Okay, so Rolle's theorem is saying when it says there exists C in AB, the meaning there is there's at least one C. It's at least gonna happen once between A and B. It has to. It might happen more than once, but it definitely happens at least one time. And when you start making some drawings, and really the key here and why you couldn't write a theorem like this until calculus was around, because we didn't have this idea of continuity or differentiability. So you can't just say this is true for any function, right? Like, because somebody could draw something with a jump or a hole or a cusp, right? And so we have to say, okay, it's continuous, and we've defined that, like, with limits, right? It's differentiable. We know what that means because we know about derivatives now, right? Now we can say it for sure. Okay, very nice. Let's do some example problems. Kind of the bread and butter problems, if you will, are things like this. Check the 3 hypotheses of Rolle's theorem. So for each of our examples below, first thing we'll do is make sure that our function satisfies those 3 hypotheses. That's critical. Like, we can't do anything, we can't make any claims unless we know it's continuous, differentiable, and that the y values of the endpoints are equal. So we'll make sure it satisfies the 3 hypotheses. If it does, if f of x on AB satisfies the theorem, find all C values that would meet the conclusion where f prime of C is equal to 0. Okay, so we'll look at f of x equals x cubed plus 3x squared minus x plus 3, a nice polynomial to start us off on the interval from -2 to 1. Then we'll also look at this piecewise function right there, 1 plus x where x is less than 0, 1 minus x where x is greater than or equal to 0 from -3 to 3. Okay, sounds good. Hop over to my paper here. Okay, I've already got it written out. Make sure I did that for this one ahead of time. Check the hypotheses. If it satisfies the 3 hypotheses, then find the C values. We'll start with f of x equals x cubed plus 3x squared minus x plus 3 on the interval from -2 to 1. Okay, so the first hypothesis was that f of x is continuous on our interval. So we'll say on -2 to 1. All right. So we're going to put like question mark, right? Is it continuous? Okay, so for this first hypothesis, there's really not any math to do. Just look at it. Okay. For this function, does anything like weird happen between -2 and 1? Right? Are there any holes? Are there any jumps? Are there any vertical asymptotes? No, right? We're never dividing by 0, which would indicate a hole or a vertical asymptote. And there's no jumps, right? And a piecewise function might have a jump, but this is not a piecewise, so we're good. There's nothing to really calculate there. Okay. Number 2 is f of x differentiable on our interval? And now technically it's the open interval that uses parentheses because we don't care about the endpoints themselves. Here there is a little something to do, right? Differentiability is all about the derivative. Does the derivative exist? So let's find the derivative, right? 3x squared plus 6x minus 1. Once we have the derivative, then we're kind of thinking along the same lines as the first hypothesis. Will this derivative have any holes or jumps or divide by 0 or anything like that? Well, no, in this case, not at all, right? It's another polynomial, so nothing bizarre, nothing unusual happening between -2 and 1. So this is a check as well. Not a whole lot to do. Be careful though, right? You definitely got to check these, and obviously we will encounter some that don't meet all. Okay, the last thing, now there's some calculations. Do the y values of our endpoints equal each other? Are those really equal? F of -2 and f of 1. Okay, hopefully they do. Let's check out f of -2, plugging it in to our function, x cubed plus 3x squared minus x plus 3. So I did that and I got 5. I did that calculation. Then we'll check f of 1. I could probably, let's see, we could do that. 1 plus 3 is 4, minus 1 is back to 3. Wait a second. Is this really? 1 plus 3 is 4. Minus 1 is 3. Wait a second. This is supposed to work. What happened here? These are supposed to both be 5. But that's coming out as 6. Uh-oh. This is kind of embarrassing. I thought I've been doing this same example for quite some time. Okay, just kind of, I'll be back in a second. Okay, something is definitely going on here because I'm not even getting this answer for -2. What if I wonder if that should have been a 2. I'm kind of -2 to the third plus 2 times -2 squared minus -2 plus 3. Okay. Aha. Let's make that a 2 instead. My mistake. So when we plug in -2, I do get 5. And if I plug in 1, that would be 1 plus 2 is 3, minus 1 is back to 2, plus 3, that would also be 5. Okay, perfect. And that would change our derivative to a 4 right here. Haha. So with a little little correction there, this does satisfy the 3 hypotheses of Rolle's theorem. Like I wanted it to in this case. All right, now since it satisfies Rolle's theorem, we are supposed to find all the C values such that f prime C equals 0. All right. Well, let's take a look. We have our derivative there, where essentially we're just figuring out where will that derivative equal 0. And we should come up with an answer that's in the interval. That's what Rolle's theorem is telling us must be true. Okay. Well, just looking at this, I'm not sure if this will factor. It might, but I'm just going to go ahead and go with quadratic formula. So x equals -b plus or minus square root b squared minus 4ac all over 2a. See what we get, -4. This will give us 2 solutions. Let's see here. No, I'm getting a radical there, radical 28. So it would not have factored. Let's see, this can be simplified a little bit. I can pull out a 4. Make it plus or minus 2 square root 7 over 6. Okay, so we're looking at -4 plus Oh, then we can reduce everything by 2, can't we? Let's go over here. -2 plus or minus square root 7 over 3 if we divided 2 out from all of them. All right. -2 plus or minus square root. Let's look at them one at a time. -2 plus square root 7 over 3. And -2 minus square root 7 over 3. Now, at least one of these, maybe both, but at least one is going to be in our interval. Just looking at them, it's hard to tell. But what I'm going to do is grab my calculator and just kind of plug them in, see what decimals I get. Okay, so this first one, I got this one is just about 0.22 if I round. That would be in the interval. How about the other one? -2 minus square root of 7 divided by 3. This one, they're both, this is -0.155. So both of these solutions are in the interval. From -2 to 1. So we have 2 answers there. Interesting. Okay. We had a part B as well. Hopefully that one also will work out the way that I hope. Part B was f of x equals 1 plus x, x less than 0, 1 minus x, x greater than or equal to 0, and the interval was from -3 to 3. Okay, so when you have a piecewise, right, there's a possibility that there's a jump. There may or may not be one. You gotta take a look. So first condition, first hypothesis, is f of x continuous on -3 to 3? And we're not immediately sure. Okay, the only possible issue is where it switches at 0. Check at x equals 0. How are we going to do that? We're going to take the limit from both sides. We're going to take the limit as x approaches 0 from the left. From the left, we would use the first piece. Okay. And we're going to check the limit as x approaches 0 from the right. And these need to be the same. And the function value needs to equal that as well to be continuous. Okay, so from the left, all we got to do is plug in 0 and we get 1. From the right, hey, plug in 0, we also get 1. So we know from this that the two-sided limit is equal to 1. Also, we need to check f of 0, make sure that that's equal to our limit value as well. Well, f of 0 is where it's possibly equal. So that's equal to 1 as well when we plug in there. So all this is good. Those are equal to one another, right? So we know it's continuous. Wow. Okay. Hypothesis number 2, is it differentiable? On -3 to 3. Well, just because it's continuous does not mean it's differentiable. And it turns out here, it's not going to be differentiable at 0. Why is that? If you can kind of see, like, if you took f prime, we never did derivatives of piecewise functions. It's not anything all that difficult to do. You just take the derivative of both pieces separately. So the derivative of this first piece would be 1. but the derivative of this other piece would be -1. And so there's a problem. I shouldn't write or equal to. I should just write greater than. There's a problem at x equals 0. There's a cusp, because that's the moment where it switches. If you were to draw this, it might be a little more clear. So what's happening with our original function, 1 plus x has this positive slope, right? And it's going to hit at 1. So if we have, this is like y equals x plus 1 or 1 plus x. Okay. Then it switches to this negative x plus 1. So they have the same y-intercept, but now the slope changes. And it's continuous, right? But it's not differentiable. So that is not satisfied. And so we cannot go any further. This does not satisfy Rolle's theorem. In other words, the conclusion is not guaranteed. If we were to be like, oh, well, you know, will this, you know, is it possible that the function will still have a place where the derivative equals 0 on the interval? I mean, it's possible, but it's not guaranteed anymore. You know, -3 to 3 would be symmetrical here. But we can see, yeah, there's nowhere where the derivative equals 0. It does hit a max, so it's able to, you know, get back to the same y value that it started at. That would be true, but it's because of the cusp. That nowhere does it equal 0. Okay, very nice. It's good that we looked at one of each and got to have some fun with part A. That was entertaining. Let's stop this video here, and we'll see the mean value theorem next.